Ladies and gentlemen, hello and welcome back once again to the briefing room. My name is Eric Cavanaugh. I will be your moderator for today's event in which we're going to talk about an absolutely fascinating concept, folks. The actual title for the event today is The Perfect Storm, the Impact of Analytics, Big Data, and Cloud. And of course, that is one mighty nexus right there, folks. And we're going to talk about the impact on data itself, on storing data, on accessing data, the foundation, of course, of information management, which is that database. And we're going to talk about some of the popular concepts in database management, of course, like SQL, the structured query language. We've heard a lot about NoSQL these days, which usually means not only SQL, but also means not SQL. Some fair amount of confusion in the marketplace about that. And, of course, you can go to databaserevolution.com for some information about database and what's happening in that field, and there is a lot happening, to say the least. So there is a slide about, oops, actually I have to make myself the controller here. So hang on one second. So there is a slide about yours truly, and enough about me. So the mission, as many of you now know, in the briefing room is to reveal the essential characteristics of enterprise software. And frankly, this show grew out of a desire on my part to really find a way to find a format and a forum where we could strip away a lot of the marketing language and really understand the nuts and bolts of these technologies. Because as many of you know, certainly who have been in this industry, it is not the easiest thing in the world to look at a company's website, even review their materials, and fully understand what it is that they're offering. So the idea is that we will pair innovative vendors with seasoned veteran analysts in a live analyst briefing. So one of the keys to our format is that the analyst and vendor do not coordinate before the show. And the reason we do that is because if they did coordinate before the show, then the analyst would know all the questions beforehand, and it just sounds kind of like an infomercial, which is not terribly interesting. So they do not coordinate it, and that way we get nice organic questions, the kind of questions that the analyst would ask in a briefing. So that's why it's called the briefing room, is because we really do expose a live analyst briefing. So October is Database Month. We cover a different topic each month, primarily because from the audience perspective, that gives you the ability to do some apples-to-apples comparisons of various products in a particular space. So next month we'll do cloud. December is a catch-all month. That's innovators. January, we're right back to big data. So let's move on here, and I hear a busy signal. Okay. Database. So, of course, database has been around for quite a long time now. In fact, Jim Starkey, who is working with Barry Morris from NuoDB, is one of the most veteran database architects in the world. He was feeling a bit under the weather today, so he's not going to be with us, but Barry Morris is standing in for him. And you can look him up online and see the amazing things that Jim has done over the years. He is, as I say, a true pioneer in the database field. As many of you know, on some other shows, we've also had folks like Michael Stonebreaker on DM Radio and some of the other real veterans of the field. And these guys have been around. They've learned the ropes. They know how these things work. And we're going to hear about this new design for a database, because typically databases, you've just had to go and buy bigger machines to get faster performance. But now, of course, there's this whole scale-out paradigm of the cloud where you just add more and more machines, but it's not always the easiest thing in the universe to do. So we're also very pleased to have Dr. Barry Devlin, founder of the data warehousing industry by any number of accounts. He's been doing this stuff for a very, very long time. He's very well respected. He's a consultant, so he goes out there and actually does this stuff. He doesn't just talk about it. We're very pleased to have him calling in all the way from South Africa, as a matter of fact. So NuoDB, what is NuoDB? It is an ACID-compliant NoSQL relational database. So as I mentioned, a lot of these NoSQL databases, well, they were designed to circumvent some of the constraints around a relational database. And, of course, ACID compliance is one of the critical aspects of any transactional database system. You want to make sure that you're ACID compliant so you don't lose stuff, so you keep track of things, so that everything works well, and you know that it's going to work well. It's what you might call enterprise ready. But this is a different architecture, so it's architected to scale on the cloud, and it's basically a peer-to-peer messaging system that acts like a database. So I think this is just fascinating stuff. So So there's Barry Morris. Barry is an accomplished software CEO with over 25 years of experience. He was at Streambase. We were talking about that before the show. And, folks, we discovered actually on the pre-call today that both Barrys are from South Africa. So hopefully they weren't in cahoots here. I'm just kidding. But I'm going to hand it over to Barry Morris to take it from here. So, Barry, I'm handing you the keys right now. And the keys are now in, hold on. The keys are now in your hands. So, Barry Morris, go ahead.
Great. Thanks very much, Eric. I hope everybody can hear me. And I want to just start off by apologizing on Jim's behalf that he did very much want to be here today. And, of course, he has a much deeper understanding of how the technology works than I do. Having said that, I feel that I can give you a good level of introduction and I hope can answer your questions as we go through this. I'm going to spend the next 20 minutes just taking you through an overview of the product, both in terms of its context, but also in terms of how it works. And I hope we can get deep enough into that today for your needs. So just as a summary, for those of you that want a summary up front, we think of the product as the database for the 21st century. And implicitly, what you have today is a database that's not only of the 20th century, but is probably designed 30 years ago in terms of its original architecture. And so the list of things here, it's a revolutionary database system based on something called emergence. We'll talk about that. It's designed for the cloud. It's designed for scale-out and commodity data centers. And it can do, to first approximation, anything that you can do with a traditional relational database management system. The interesting thing, of course, is what it can do beyond that, and we're going to talk about that. But the essence of those things is that it's cloud kinds of characteristics. So I've got just a slide here quickly on the 20th century database. A few years ago, we had a consolidated market, really just 5 players that owned the entire market. And what did those systems have? Well, they had SQL, a powerful and standardized query language with lots of industry standard support, tool support, skills in your organization, and so on. In a sense, that's the railway network that was laid. It's been wonderfully successful. It's arguably the most successful technology in our industry ever. And I don't think there's any other language that after 30 years is still being used in new systems. With it, you get data guarantees from asset transactions. You get, as I mentioned, the ecosystem that's out there. Very powerful systems, and they really held sway for a very long time. And you might say, so why didn't it just become like the microprocessor industry, just a sort of a consolidation around 1 or 2 players, and the game is over? And the answer really is depicted here. It is that the things on the right, which are these powerful characteristics of these traditional database systems, are not enough for the 21st century. And the things on the left, I think, give you an idea of what we're talking about. These are systems that historically scale up and only scale up. So you want them to go faster, you buy a bigger machine, period. That's a huge problem because everybody's going to cloud and going to kind of private cloud and commodity data centers and virtualization and all that stuff. What you want is on-demand capacity. You want to be able to add machines and go faster. And that's just not what these systems do. You also, in those systems, want to be able to essentially share resources between different systems. And again, that's not part of the original design center of these older database systems. We all know about and have different views of big data. But if you were around in the 80s and you sort of looked at what some of those database systems were handling, you might find this amusing, but a big database was a gigabyte database in those days. Today we think that's quite laughable, but that's the truth. These are systems that were designed for much, much smaller database sizes than what we're dealing with today. In terms of modern workloads, we're talking about huge concurrency, we're talking about enormous transaction rates, very low latency response. Again, I recall a date paper in the 80s where there was a discussion about whether or not there were applications in the world that needed 1,000 transactions per second. It's surprising how modern workloads are many orders of magnitude much bigger than that. And so we need a new system for that. We need 24/7 operation. That means not just a highly resilient system that will stay up amidst lots of failure, but also a system that can do rolling upgrades and so on, more or less a system that you can start today and run for the next 10 years without ever taking it down. That's the kind of expectation people have, and those traditional database systems don't come remotely close to being able to do that. Geo-distribution is kind of obvious. You want a single database running in Tokyo and London and New York, consistent and coherent, and if a database or if a data center goes away, you fail over. And lastly, you don't want to have a database system that requires negotiation with IT in order to get a server up. You want to be able to run it on your laptop, build applications, deploy those applications. So these are systems that are actually very powerful, but today they don't meet a wide range of needs for current systems. And if you look, slide 5, I'll just skip over this briefly. It's not really sort of worth spending too much time on it, but if you look at what people are doing in terms of building operational database systems out there, they've got really very ugly and complex architectures. They're putting caches in front of these systems. They've got master-slave replication. They're doing sharding. They're doing partitioning. They're doing all sorts of stuff, most of which is extremely complex and fragile. That's not what you want. What you want is a system in which you just add more machines and it goes faster. So enter Jim Starkey. We talked about him briefly a moment ago. Jim is a name to conjure with in the space, probably one of the top 2 or 3 database scientists in the world. He was the inventor of the first DEC, relational database system, RDB-ELN, but also of Interbase and Firebird, the Falcon storage engine for MySQL. He was the inventor of blobs, the inventor of MVCC, and so on. And so a guy that's done it all, but not just that, is one of the deep innovators, the guy with 10,000 hours in database systems. And Jim really sort of took a look at the problem of what the issue was. And the issue, of course, was not just that I suppose the question was, is it SQL that doesn't scale? And SQL being a declarative language, if you were going to design a language to scale, a declarative language might be what you would choose. So it's not SQL. And I guess the second question was, is it transactions? And he set about proving that transactions are not non-scalable. And where he came out is really, to paraphrase Bill Clinton, is the notion that it's the architecture, stupid. That the problem is databases of all sorts, SQL and not SQL, have for 30 years or more been designed essentially as kind of grown-up file systems, mechanisms for giving you sort of concurrent access to a disk file. And that design inherently doesn't give you these kinds of cloud characteristics that we're looking for. He came up instead with a thing called emergence, and emergence is something you've seen in nature. It's the way that flocks of birds fly. They fly together, they take off together, they land together, they go south for the winter, and yet they do it with no single bird in control. It's a meaningless question to say, where is the brain in the flock? Because there is no single point where the decisions are being made. They're being made in a collaborative way. And that notion, which is pervasive in nature, by the way, in fact, it's the only way that nature builds large-scale systems, is what Jim used as the core architecture of the system. So instead of having a monolithic, centralized, synchronous kind of a model, the NuoDB architecture is designed around a loosely coupled, asynchronous, collaborative, and peer-to-peer kind of an idea. We haven't got a lot of time to talk about all of that right now. I'm going to just quickly skip over a few slides to give you an idea of the fact that it does work before I talk about how it works. Here you see it running on one machine compared to MySQL running on one machine, and you see us doing between 2 and 20 times the performance on a single machine. It's not obviously the purpose of the system to run on one machine. The whole idea is to run on more. Here you see it running on 2, and the second machine is added sort of partway down this timeline. By the way, the entire timeline left to right is about 10 to 15 seconds. So you see an immediate increase in performance, in this case more than 100% for caching reasons, by adding a second machine. These machines are like the birds. If you take away the second machine, it'll go back to the original performance. But more surprisingly, you could take away the first machine, because just like birds in a flock, there isn't a master machine and a slave machine. They're actually peers of each other, and you can take away any of the machines. It'll keep running. Here you see it's the same thing with adding a third machine. It's not quite such a pretty chart, but you see the same thing happening. It goes 5,000, 10,000, 15,000 transactions per second on pretty low-level hardware, by the way. And in fact, we can do that. Here you see it happening on going to 9 machines. If you look in the top left table, you'll see we're running here at 27,000 transactions per second on 9 machines. MySQL running at 3,000 on one of those same machines. And this is a load. If you look at the bottom left, this is a 50% update load. So we're not cheating here. This is a standard load, and you see it scaling and scaling. By the way, we can do the same thing on EC2. So here you see the chart of it running on EC2. Quite a surprise for those of you that are aware of the network latency unpredictability on something like EC2. And it's because of this asynchronous messaging architecture that we can actually do this. You could say, why am I only scaling out till 9? Well, you know, in the labs, we scale the thing regularly to 40, 50, 60 machines, no problem. Actually, the reality is we don't have people out there that are trying to use it at that scale because that's an extremely fast database system. And of course, it's standard SQL. And by that, I mean that you can use all your standard tools. You can use Excel, you can use your Hibernate or your JDBC drivers or Ruby Active Record, or you can use your standard tools, standard ETL tools, standard reporting tools, and so on. So just to try and kind of get to the stuff which is for the technical amongst you, the interesting piece, how does it all work? I'll draw your attention to the chart on the screen right now. And on the left-hand side, those are just applications. You know what those are. You've got these things called brokers. They're basically load balancers. Not very interesting how they work. They just allocate transactions to different machines. The two interesting tiers are the transaction tier and the storage tier. And I'm going to actually just start talking about the storage managers, and then I'll give you an idea about the transaction engines. But first, let me just mention that the transaction engines are in-memory nodes. Okay, these are just pure in-memory nodes, and the storage managers are the only place really where we're putting data on disk. The storage managers, to talk about them for a moment, are in fact key value stores. Okay, so contrary to traditional architectures, we're not storing table-structured files on the disk at all. What we're doing is storing objects in key value stores. And architecturally, we can support any key value store you want to give us. As long as it can do a put and a get and a delete, we can use it. Today, we support Amazon S3. We support Hadoop HDFS. The default is your file system. We can support that, of course. And indeed, we're looking at all the other options that are out there, of which there are many. There are enormous benefits of having a key value store backend. Don't really have much time to go into it right now, but we can talk about it perhaps later. You see that there are multiple key value stores there, and what I want to say is it's natural for people to think that we're partitioning or sharding the database. We're not. Each one of those is a full copy of the database. In other words, you can run with just one of those, in which case you're running like Oracle does. If you put a second one in, you just add it to the running database. It will fill itself up, catch up to the first one, and become a peer of the first one. When it's done that, you've got two full copies of the database, and it's redundantly running. And we can keep talking about adding those and taking those away. You can add them in different locations, and so on. Much more interesting is the transaction engine tier, which, as I say, is an in-memory tier. And running in this tier is really a set of distributed objects. Everything in the system is an object that we call an atom. And these obviously are the things that we're fetching from the key value store and that we're serializing to the store. The entire database, everything including user data like rows and tables and things, as well as indexes, as well as metadata, and as well as kind of meta-metadata, is all of that persistence data is actually sort of managed in terms of atoms. And these atoms can do magic things like replicate themselves to other machines so that you can maintain live replicas. They can store themselves to disk. They can send replication messages to replicas to say, I've been changed and these are the changes. And they can take part in transactional semantics, which of course is a key part of how the system works. And so it's actually these objects, these atoms, that are the elements that are the birds in the flock, if you like. And I'm going to give you a little bit of a quick walkthrough of how it can work, because that often gives people a sense of what's going on in the system. If a transaction comes in from the left-hand side, it's going to be allocated to one of the transaction engines by one of the brokers. Doesn't matter which broker you connect to, they're all equivalent, and you could lose any of them and it would keep going. You just connect to a different one. It's going to hand your transaction to one of the transaction engines. That transaction engine, when it first is added to the database, is just sitting there waiting for that connection. It's basically, it does no real kind of preparation of any sort. It's basically just sitting there waiting for some work. It gets given some work. At that point, it needs a list of these atoms to do some work. It loads those atoms, and it does the work. So where does it load them from? If it can, I suppose the general principle is it'll load it from the most responsive place. And obviously, if it's already got it, that's the most responsive. If it hasn't got it in memory, it's going to look at the other in-memory systems, the other machines in the transaction tier, and if it can find it there, it's going to get it from the most responsive machine. So if I need atom number 123, I'm going to find the machine that's got atom 123 that's the closest to me. And by the way, that's probably not a machine in Tokyo, that's probably a machine in Boston, if that's where I'm running. And so you've got this rapid fetch from someone else's memory if I can do it. If I fail to find it anywhere in the transaction tier, then I can go to one of the storage managers. I'll get it from the most responsive storage manager. Again, I'm not going to get it from a remote storage manager if there's one local, and I'm going to get it from there. I'm going to do the work. I'm going to hand back the results. That's the general idea. It's a little bit like a paging architecture or a caching kind of an architecture at that level. You'll notice that we're demand loading the data. We're not kind of pre-populating the data. And the real magic is the fact that we're able to keep these replicas. You know, any given atom might have 20 replicas or 200 replicas or 20,000 replicas across the cloud, and the replicas know how to keep each other up to date. The question that always comes up at this point is, okay, so how do you handle transactional semantics? That's a long conversation. That's really where the patent is. We have a patent that we got in less than a year, which is some sort of record, because no one had ever done this stuff before. And that patent really describes how we do that. The short version is that we use multi-version concurrency control, which is to say that we never actually delete a record or do a destructive update to a record. We only ever create new versions of records pointing to the old ones. And that model that model allows you to do read-write concurrency without doing network locking, because network locking is called the slow pedal. There's another mechanism that we use for global database constraints like update conflicts and uniqueness constraints. Don't have time now to talk about exactly how that works, but it is something we're happy to talk about. And so what you've got here is a system where it can be running. I can add machines to it. The new machines are simply going to be, if I add them in the transaction tier, they're going to simply start taking on some of the workload. If I take machines away, all of the machines in the transaction tier are volatiles. There's nothing about their data that can be lost to the system. At worst, what you're going to get is some failed transactions going back to the application, and that can just be reinitialized or reinitiated elsewhere. So that you can lose transaction engines happily, and the system keeps going. Storage managers equally. If you've got 2 or 3 or 4 or 10 storage managers, they're peers of each other. None of them is a single point of failure. You can lose any of them or all but one of them, and the system keeps going. So that's the general idea, and I have here for you just another picture that gives you a sort of a different cut on the same thing. The main thing to understand here is that we've got all these clever atom layers under the covers, but from the perspective of applications, they're really just seeing JDBC and ODBC and Ruby Active Record and things of that sort. I'll note again that in terms of the storage managers, they can run on top of multiple different kinds of key value stores, and they can do so concurrently. So we can support Hadoop HDFS at the same time as supporting a file system running on top of an SSD, and you get different performance characteristics by doing that. So just to finish off, if you really look at the capabilities of the system, the darker gray kind of rows in this chart at the top of the chart represent the things that you get if you've got a traditional SQL database, and they're all very powerful things. The things that are lower down are the things that are more kind of cloud-oriented and more associated with, I suppose, the simpler systems like NoSQL databases. And what you get with NuoDB is basically all of the above. So, Eric, with that, really, I'd like to hand back to you.
Okay, and I'm going to go ahead and hand the keys over to Barry Devlin, who is calling in all the way from Cape Town. So, Barry, remember, you got to speak loudly so that you project. Just click anywhere on that slide and use the down arrow on your keyboard to move your slides forward. So the floor is yours, Barry Devlin.
Thanks, Eric, and thanks to the other Barry. Yes, we've sort of crossed lines as we've got. I'm from Ireland originally, now living in Cape Town, in beautiful Cape Town, and I know that the other Barry spent some time living in Ireland, having originally come from Cape Town, so it's all quite a mix. I have only a couple of minutes here to speak to you guys, and I chose to go back to the title of this particular session about the perfect storm and the impact of analytics, big data, and cloud, and just put a few thoughts at a very high level in place before we get into some deeper questions. And in a way, you know, Barry Morris has spent some time going down into the depths of how databases work or how his database works, and it's very, very different from the traditional database for sure. But let's just reset some of the higher level stuff. As I hit the right key, we'll go to the three key trends in business that are going on at the moment. And these are the ones I see. They've been going on for a few years. Closed-loop business, to get from strategy to execution and merge the operational, informational, and collaborative areas together to get the flexibility that we want to adapt to change. We've got the big data, the massive information volume for use, and we've got the other side of it, which we're not really going to talk about today at all, which is the people side, the collaboration, the innovation side of it. And this might say, I want more, I want it now, the bigger, faster, distributed, more flexible, more personal, I want everything now type of business requirement. We've all heard it. And those are a set of requirements that are very difficult to match and to meet in today's environment, as we know. The way that we've built applications in the past, not just databases, but applications in the past have been siloed, and I think they continue to be siloed. And creating direct, immediate access to data that is consistent and that works together across those silos is always part of the infrastructure problem that we face. Now, when we look beyond the requirement, we look at the technology, and again, this will bring us into the database. Obviously, we've got areas in the application area, the SOA, the mobile apps, the analytics. Of course, that stuff's going on. But for the moment and for today, I just want to dive into the area of the databases and the big data area, in particular big data. And the reason I want to hit big data now is because I think everybody's talking about it and nobody really knows what we're talking about. I think it's time we dropped the phrase big data and started talking about data. Big data is really all data, because I have never, ever found anybody who told me this data is too big to be called small or this data is too small to be called big. It's all mixed up, and it's not really a way of thinking about it. I've been really playing with the possibility of looking at this thing in a different way, and I've come up with this picture shown here with 3 domains of data. 3 domains that are very different in their characteristics, but are all closely related. The process-mediated data down in the bottom left of this diagram, which maps flexibility against timeliness. The process-mediated data is what we might call our traditional operational and informational data that has been created through data entry and cleansing. It's the stuff we all know about. It's made in business processes of the traditional sort. And then there are these 2 other boxes, the machine-generated data and the human-sourced information, which are actually the sources of process-mediated data, but up until now we never had to worry about them. In sense, machine-generated data is, as it implies, the output of machines and sensors. It's where we get into the areas of high speed, high volumes, lots and lots of transactions, lots and lots of events actually coming through the Internet of Things. And they need to be embedded into process-mediated data. human-sourced information, the subjectively interpreted record of personal experiences, which have an unknown model before we use them, and have driven an awful lot of the thinking around the idea of NoSQL and the various big data type of systems that we've been talking about for a few years. In the time I have, I can't really go much deeper than that, but I have given you a link to a white paper just here on the page in bit.ly big_data_zoo. Have a look at that, and you can dive into that and send me emails and ask me questions about it as you see fit. Let's talk about a little bit about the technology that underlies what's going on, the changes that are going on. And I just have taken this from a very simplistic point of view of it's about hardware, it's about software. The vast improvements in price, performance, and memory have really brought us to a stage where main memory in our computers, I believe, is getting to the stage where it can hold all of the critical data for most businesses. Now, clearly, I'm not talking about the Amazons and the Facebooks and the Googles of this world, which are the ones that everybody talks about. I'm talking about the mid-sized businesses, the small, medium-sized businesses, even the large businesses, even some of the enterprise businesses. I believe we're really beginning to think about the possibility of putting some or most of or all of that critical data and fitting it into main memory. And that's a very different model, a very different architecture from a traditional database design, which is disk-centric. So in that sense, on those things, commit means on disk. And disk I/O bottleneck was a key design point. And I know that Barry Morris and the work that he's doing has moved away from that. And I think this is a great point to make. But it's not the only point. Another point that we have to look at is the fact that we've moved to the stage where we're no longer capable, because of physics, of making our single processors go faster. And that's been happening for some time. We've moved to the multi-core, multi-processing arena, which means the traditional programming on a single CPU-centric approach is no longer viable. We need to talk about MPP. We need to talk about the transaction type of environment that the other Barry has already mentioned. But we're going to have to think about it much more broadly, perhaps, than we've seen already. And finally, we have to think about the physical data representation, which is coming back to the forefront. I heard Barry mentioning the fact that he uses key value stores in NuoDB. Very good. We've seen the other debate going on between row stores and column stores, the compression ratios and possible, the idea that column stores are slow to update and rows are fast to update, et cetera, et cetera. All of those debates are coming back to the forefront of what it is we need to do to make our data bases accessible and usable today. So we're really, I think, in the area of a possible disruptive change in the database arena. And I think NuoDB is part of that question mark. I think if we go back in history a little bit, we saw that back in the early days it was hierarchical network databases, and we worked on them and we made them faster. We had the speed of record update. We were looking at physical storage optimization, and then came along relational, where we moved to a logical model of the data's relationship to reality. That, as you see in the chart, started off moving much slower and much lower performance, much fewer features than the hierarchical network databases of the day. But during the 90s, it overtook them. We had the disruptive change that Clayton Christensen talks about in The Innovator's Dilemma, and since then, relational has been king. And we're now at a stage where the question that arises is post-relational going to take over? Where the questions that are coming up that we need to deal with in this cumulative progress is the questions are flexibility and scalability. And the question, I think, is still open. Are we going to see some of these post-relational databases go to niche? And I'm sure the answer is yes. Or is one or more of them going to move to the next wave? And the question, I think, of course, for Barry Morris and NuoDB is NuoDB going to be the next wave? And I think that's going to be the interesting question, which we probably need to get to in debate. With it, I'm going to skip my last chart, which would be talking about the bigger picture of how IT and business needs to work together in this new environment, and really begin to think about some of the questions that I would like to put to Barry Morris. Eric, is that okay that we switch?
Yeah, just go ahead and dive right in and speak up a little bit if you could.
Oh, Eric, I'm speaking as loud as I can. You know, I'm 12,000 miles away.
Okay.
So let's start. And so for you, Barry Morris, I'd like to just start with this distinction or this focus that you have on the object-oriented, message-oriented, distributed nature of the database, and contrasted with in-memory operation. I mean, those two things sound to me to be working in different directions to some extent. And I'm wondering what you feel when I propose that with this memory price performance improvements that we've got, the possibility many of the databases will be able to fit all business critical data in memory. Why do you need both of these technologies?
Okay, hope you can hear me, everybody. Of course, one of the things that Jim looked at the time of designing this new architecture was to try and understand where are we going in terms of systems and particularly price performance of various parts of the system. And one of the most important elements of that, and maybe the most important, is RAM prices and the inevitability of essentially lots of free distributed RAM. The interesting part, though, for him was the distributed part, which is, of course, we can create a gigantic machine with an enormous amount of RAM and run a database in that one machine. But how much more interesting if you've got 300,000 small machines, all of which have got a fair amount of memory, and how can you use that not just to sort of put different parts of a database on different machines for use by different users, but in particular, and maybe this is a direct answer to your question, Barry, is that in this kind of an architecture, you can have the same database fully in RAM multiple times in multiple parts of the world, and it'll be keeping itself consistent. And the mechanism for doing that is this object-based system. And so one way of thinking about the database is that it's upside down, that the database really is in memory in some sense, and that the storage is a way of tracking what's going on in memory, whereas the traditional view of a database is that the database is on the disk and that you're temporarily putting it in memory.
Okay, that makes sense. Certainly the idea of being able to have multiple copies of the database in different parts of the world sounds like a very useful concept for multinational companies and for large organizations that need that sort of distributed work. But what's the advantage for the small and medium-sized enterprise?
Okay, perhaps I should have taken that first. Let's take an example, which is a canonical example of somebody running maybe a website or something, and they've got 50,000 concurrent users or 500,000 concurrent users or something. What those users want is to have very low latency access to that data. That data might exist in some set of objects, you know, atom number 123 and atom number 719 and so on. And that atom could be replicated as many times as you like on lots of small machines, where each machine is effectively supporting one or a small number of users. And so the idea here is very much that it gives you all of the benefits of in-memory, but that it allows you to replicate parts of the system onto lots of different machines on a demand basis. That gives you enormously more performance of various sorts, but critically for a website, gives you much better latency benefits.
Okay, I get you. So you mentioned this in your presentation and sort of glossed over it a little bit, and it was one of the concerns that came up for me when I was looking at your slides, and that seems to be that, you know, disk storage and the I/O speed of disk storage was always the problem for traditional databases, and it seems now that you're sort of replacing that disk storage I/O with a distributed computer memory storage, which is how the failback, and then finally with your storage managers failing back to disk. And it seems you're replacing disk I/O latency with network latencies. And I would have thought that there were significant concerns around network latency. Okay,
good, very good question. If you spoke to Jim about this, what he would say is that really he was thinking about memory hierarchy. If you're thinking about the notion of going from registers to cache to RAM and very down to disk and tape or whatever, you could think about what we've done as to introduce another layer of kind of memory hierarchy into the system, which is distributed memory or remote memory, if you want to think about it like that. And so it is true that we get the opportunity when we're looking for a particular, in this case, an atom, we get the opportunity to fetch it from another machine's memory very rapidly. That's about 100 microsecond round trip on a gigabit Ethernet, and so that can be done maybe 100 times faster than getting it from any kind of disk storage. Furthermore, for many database workloads, you have a working set that can end up fully in memory or indeed replicated in memory. And that's not necessarily the whole database. Typically, you find that it's a small proportion of the database. When that's the case, the system ends up running effectively as an in-memory database system with distributed caching. And that's vastly faster, by orders of magnitude, than trying to go to disk. Now, of course, and maybe you want to move on to this, but of course we have to be able to commit to disk. Of course, we have to be able to guarantee storage on disk and so on. But we are moving a lot of the work into the free RAM that you were talking about earlier.
I get the free RAM. I get the idea of moving it into memory, and I think that's actually a very important point. But before moving away along that particular route, I'd just like to go back to this network latency. I mean, maybe it's just the fact that I'm now in South Africa and broadband isn't that broad, but I can imagine that network latency can be quite a problem, surely.
Well, again, the latency on a typical sort of machine-to-machine communication on a gigabit Ethernet, not even a 10 gig Ethernet, is going to be of the order of 100 microseconds, and that's very considerably less latency than disk latency, which is measured in milliseconds. And so the answer is, of course, there's latency as compared to not having to fetch the data at all. But it's very considerably less latency than getting it from anywhere else. And so it actually turns out that we're getting significant performance benefits out of that.
I can imagine that's true within the confines of a compute center or within the confines of IBM called them CACs, I think they are. But I mean, aren't you talking about going to a more distributed, worldwide, global sort of environment using machines in different time zones?
Sure, yes. And so that becomes another interesting topic. So what happens when you do introduce, at least in part of the system, a network with poorer latency? And to understand that fully, you really have to go a little bit deeper into how the architecture works. But what I'll say is this, that the messaging in the system is batched and asynchronous. And so if we had a network lock manager, and we had a system running across, let's say Paris to Boston, the network lock manager would need to lock a particular record that exists in both locations if either one wants to update that data. That's extremely slow. It's going to go not only at the speed of the slowest machine, but at the speed of the network. If what you're doing is doing this using asynchronous batched communications, you have still got network latency dependencies, but they're significantly less. And so, you'd need to go into exactly how that all works to understand it, but the combination of asynchronous messaging and versioning is what allows us to do that on a LAN, or at least a WAN basis, and also it's the same issue in EC2 or some other unpredictable latency cloud environment.
Okay, let's leave network latency aside for the moment. I've seen a couple of questions come in sort of comparing NuoDB to various different, how does this compare to this database and that database. The one that came to my mind was SAP HANA. How do you position yourself against SAP HANA?
I think that SAP HANA, as you would know, is essentially an in-memory database that is designed around the idea of being able to configure row-based or column-based storage, and thereby to give you the ability to do both operational and analytical workloads. That's essentially where they're going with it. And it's very good at that. But what it isn't, and I'll go back to one of your previous slides, you talk about scalability and flexibility. We're talking about on-demand scale-out and very flexible deployment alternatives. And so if you're wanting to run 10,000 databases on 1,000 machines and dynamically allocate those machines to databases at different times of the day, that's what we do naturally. That kind of flexibility and fluidity of how you're applying resources is where the core value is. Of course, if you want to run us as an in-memory database, we can do that. Architecturally, we can do anything that HANA does. But we're not really positioned that way. What this is about is, on the cloud, it's all about on-demand computing, and that's what the product uniquely achieves.
Okay, that makes sense. So maybe that negates my next question, but I'm really interested in the idea of the split between the old split between the operational and informational environments, and you mentioned that in the case of SAP HANA as something they want to address. But do you have a view on are we coming to the end of this split between operational and informational? Do you see NuoDB playing into fixing some of those problems?
I very much believe that. I think that that's where things are going. I don't doubt that there are going to be large batch-based processes that do gigantic amounts of data analysis in the background. We'll have that, no doubt, forever. But for the vast majority of customers, the need for doing analytics that are more or less real time, analytics on operational data, and being able to do that within the same kind of infrastructure, that's a very powerful capability. In our case, if you go back to the diagram I was describing in the architecture, you can imagine if a long-running workload came in, like a BI query or analytics query or something, came into the system, what it's going to end up doing is locking up a few machines as they go off and start providing results for that query. The rest of the system doesn't really even know about that work going on. And in fact, because of the semantics of it, they're going to be working on a snapshot that was current as of when they started that analytics query. So this is a system that's extremely good for doing exactly what you're describing, for doing kind of long-running analytics-style queries in an operational running database. It does that very well. And we haven't really announced, obviously, where we're going with this, but the architecture is really a service-oriented architecture. These nodes, as long as they obey the protocols, can exist within the system. And you can easily imagine how specialized nodes could be introduced into the system that, as long as they talk the same network protocols, are able to do all sorts of specialized things, which might be around differences between column and row storage. They might be about integration with sort of very high-end back-end systems or whatever. They would simply be integrated into the same system with the same query mechanisms and everything.
Oh, that's very interesting, and it sort of leads me on a little bit to I guess, given the time, probably my final question, which is around this big data area. I mean, I don't know what you felt about the picture that I put up of splitting big data into 3 domains, but I see some very different types of data, and most of what we've talked about was very much the traditional sort of process-oriented or process-sourced data that I've talked about in my presentation, process-mediated data. I've forgotten my own terminology. Most of that seems to be what you were talking about insofar as you're talking about traditional SQL type of processing. But do you see yourself getting into the more unstructured, less well-modeled type of data? When you use the word big data, what do you mean, and where does big data fit in the NuoDB world?
Very much agree with your notion that big data is really just data, and that at any given point in time, we always think that our data is big, but of course, looking back, it doesn't look as big as we thought of it at the time. So I think there's no question that we'd agree with that. The immediacy of data is the area that we really think is going to become more important, and the ability to get at analytics as quickly as possible and to take kind of real-time decisions about them is something that we really care about. But you asked about different data types. Of course, the system, I mean, Jim being the inventor of blobs, the system can handle anything at that kind of level. We do not, in the first release of the product, which is due out later this year, we do not have more sophisticated support for, if you like, unstructured data. But I'll tell you something which may sort of give you a hint of where this could go. The SQL aspect of the system is really only a personality layered on top of these atoms I described. And the underlying transactional architecture really doesn't know it's part of a SQL database. It could just as well be part of a document database or a graph database or anything you like. And so very, very flexible from the perspective of where this could go. The SQL choice is merely one that's based on the idea that there's a $35 billion SQL market and about a $0 billion NoSQL market.
Barry, thank you so much. I mean, I think you've really shown quite an interesting product. I mean, I think there are so many possibilities in here. It's fascinating what you've discussed. I'd like to just hand back to Eric and maybe handle some of the questions that have come in on the line.
Yes, indeed. I'm going to go ahead and push this architecture slide again so we can look at it while we're going through some of these questions. But thank you, Barry Devlin, for some good questions. And we do have some great ones from the audience here. So let me just kind of start from the top here in our Q&A panel, and I'll start moving down. So, yeah, as Barry Devlin mentioned, there were a couple questions about how you compare yourself to some of the other tools in the marketplace, such as MongoDB, Netezza, and there was one other one that was mentioned as well. Can you kind of speak to differentiation as well as you understand these other technologies?
Yeah, sure. And I don't particularly want to comment on particular products, but what I would say is that firstly on the topic of kind of NoSQL databases, document-oriented databases, clearly there's a place for them. I think everybody involved in them would say there's a benefit in having simpler solutions for certain kinds of applications, and that's what they are. They're simpler solutions. They're record-oriented. And there's I think, been proven over a period of many years that for general-purpose mainstream database systems, the right level of abstraction is set-based access to data. Once you get into set-based access for data, there's really only one choice for languages. It's not a particularly brilliant one, but SQL is what we have. It's set-based access to data, and that's where the world is going to be, I think, for mainstream database management. And if you ask me, people that do not have both SQL and transactions in their systems are either going to have to keep out of the mainstream or they're going to have to build those capabilities. I think we're already seeing some of that happening. The second topic was about Netezza, and Netezza, of course, is a very successful classic warehousing kind of solution. And those systems are optimized really for analytics and big data and sort of SQL-based analytics. We're really not positioning ourselves to take on those problems. Architecturally, we could. We do obviously run on top of Hadoop HDFS that gives us the ability to handle very large data sets, but we're not optimized today to handle kind of batch-oriented analytic workloads. Maybe that's something for the future.
Oh, that's interesting. So one of the other questions was, where is the sweet spot for NuoDB and where is not the sweet spot? And I think you just kind of answered that question, right? And I think you also gave some hints when you talked about focusing on the immediacy of data. So you're really trying to focus on real-time needs, very fast access across, even global environments, that kind of thing, right?
Yeah, if you think of us as an operational database that can go some way into analytics as part of that operational database, I think you've got a good idea. And that, to some extent, is as a kind of a plug replacement for traditional SQL types of stores, except it runs on the cloud. Think about it like that.
Mm-hmm. And so just real quick, on this architecture slide, help us understand, basically each one of these atoms has all these different pieces. Is that right?
No. So just to dive quickly into the kind of atom notion, an atom could be anything from rows in a table. Those would be stored in a certain type of atom. There are about 12 types of atoms. There are other atoms that store index data. There are other atoms that store catalogs, which is kind of the name service or the directory service for where all the atoms are in the cloud. And so atoms really represent everything. They have 12 or so different types, but they're all managed in the same way. They all know how to replicate themselves, and none of them are sort of centralized or a single point of failure.
Oh, I see. Okay, good. I'm glad I asked that question. Okay, so one of the attendees writes, if there is no master database, or is there, how are the different time zones and network latencies handled, bearing in mind sequence of events in the updates to an atom, row, object, etc.?
There's a long answer and a short answer to that, and the short answer takes about 8 hours. But we'd be very happy to talk to you about that. The short answer really is that we're handling it by understanding sequences of messages extremely well. We're handling it by the fact that what we're guaranteeing you is that the database is consistent when you look at it. So it's a kind of an observer-based consistency, and you can only look at it from inside a transaction. As long as we can give you that, the database is indistinguishable from a database that's not consistent, or at least it is consistent if it looks consistent, is the model that we're operating on, and we guarantee you that.
Okay. Here's an interesting question from an attendee who simply writes, I was wondering if there will be some feature for segmenting the data across sites, the typical example being a retailer's stores and the headquarters. I presume they mean sort of intelligently segmenting the data to different locations for, let's say, a multinational retailer or even just a national retailer with stores all around the country.
Today, we don't have what I think the person's asking for. If you had 500 or 5,000, 5,000 is actually the number for one of the customers we're working with, and you wanted to have the data stored in all locations, you would be storing the full database in all locations, but you would not be doing real-time updates of data in all locations because you typically have local updates of local data. But we do not partition the database.
Okay, good answer. Another question says, although this is the first version, as a percentage roughly, how many of the traditional properties of a relational database do you now support? And then the questioner goes on, for example, when you reach an execute block feature.
Yeah, it's a hard answer. It's a hard question to answer. What we've found is that people have ported very sophisticated, 20-year-old code bases that run on traditional databases quite readily to the system. We've got a very rich SQL 92 implementation with 99 extensions and a lot of our own extensions. And really it boils down to the details of what exactly you're looking for. Naturally, over time, it's going to get richer and richer, and as I've implied, as we're targeting the 21st century database, we're not really just trying to be, a better 20th century database. We're really adding in a lot of new interesting features that you're going to start seeing post version 1.
Yep, okay, good. And I know you were talking about cloud. I'm going to go ahead and push some of these earlier slides because I think this is some really interesting stuff. So let's see, here's with a single node. Here, of course, is adding a second machine. Here is adding a third machine. And what you really want is to be able to get that consistent improvement in speed as you add nodes, right? Can you just talk a bit more about how you're able to pull that off? I'm guessing it's because of the architecture, but could you just kind of give a little bit more detail on that?
Sure, yeah. When you add a new node, let's talk about transaction nodes. So you add a new transaction node, it needs security credentials to take part in the database. It connects, it loads up a sort of a replica of the name service, which is the catalog atom, and then it sits there and waits for work. And if there's lots of work, what you're going to get is that a broker is going to give it some work, and it's going to carry on in parallel with the others. There's a good chance that as it needs to get data, it's going to be able to get it from the memory of the existing nodes, and so the warm-up time can be very quick indeed. and it ends up carrying a proportion of the load, and that's how you get this kind of linear scale out.
Yeah, that's very interesting stuff. Okay, well, I'll tell you what, we've gone through an entire hour here. I'm looking through the questions to see if I missed one. I think I got to all of them. And you say there's another, you mentioned another version that's going to come out next year, is that right? Where you'll have more support for so-called big data?
Yeah, we haven't announced our roadmap at this point. In fact, we haven't announced the shipping date of version 1, although you would see that happen before the end of this year. We have over 2,000 users as of today, and we're going to be launching version 1 later this year. That's going to be a rich SQL database. Later next year, you're going to see some very innovative features start coming into the product. That's just who we are. We think of ourselves as the innovators in the space.
Right, and we have one last question I'll throw to you, and I know you've talked about this, but it's a good closing statement, I think, to let people really kind of grab hold of what you're talking about. One of the attendees simply writes, if I have multiple copies of a database and one is updated, how are the others synced up? And I guess one question I've got is that optimizer, I'm guessing that like a query optimizer, does it check for latencies? Because as you mentioned, if you have data persisted in, let's say, 3 areas around the world, one is in South Africa where Barry Devlin's network is not running so fast, one is in New York where it's actually running very fast, one is in London. I'm guessing that you're keeping track of latencies at different data centers or different locations, right?
Yeah, and it's not a query optimizer issue, but that is what happens. What happens is that there are cost functions running in the system at all times so that people know how responsive a particular machine is, and they know whether to get something from that machine or not. That's a separate question from the one about how we keep everything in sync, which, again, is quite a complex topic. But it's not that these back-end systems are replicating between each other in a traditional page-based replication fashion. You should think of them more as systems that are monitoring what's going on in the database and storing the results. The magic is not around there. The magic is around how the commit protocol works, and that's a much longer conversation.
Yeah, well, it kind of reminds me of change data capture versus ETL, right? In other words, you're not trying to move the entire stack of data over every, hour, month, week, whatever the period of time may be. You're doing a much more intelligent and strategic replication of data that is only focused on things that changed or something along those lines, right?
Yes, it's very fine-grained. Any given replication message is perhaps 20 bytes in size, and as I say, they're batched to network-efficient sizes and sent as a batched network communication asynchronously.
I see. That makes a lot of sense. Yep. Okay. Wow. Great content today, folks. Big thank you to our presenters. You can see some upcoming topics we've got going on. Database is this month, of course. We have one more next week. The time is just flying by, isn't it? I posted a link to the archives. Yes, we do archive all of these briefing rooms for later viewing, so you can share them with your friends and colleagues. And with that, we're going to bid you farewell, folks. Thank you so much for your time and attention. We really do appreciate all these great questions, too, from the attendees. They help us make sure the content is top-notch. So thanks again, folks. We'll bid you farewell. Take care. Bye-bye.